We'll start today with a review problem. So it says in 1 minute, 720 coulombs of charge flows through the wire in a car engine. Now, if we want to calculate the current, we use I is delta Q over delta T. And we're interested in the current there, so that's pretty good. We're all set up. 720 coulombs and in 1 minute, so that's 60 seconds. So I think we could easily see that that's 12 amps, and that's quite a strong current. Now we might want to calculate, well, how many electrons flowed in that 1 minute? We know 720 coulombs and 1.60 times 10 to the minus 19th coulombs is one little electron. So 4.50 times 10 to the 21st electrons flowed. So after that review problem, we'll move into some new material. Ohm's law. Very, very important for everything we're going to do moving forward with circuits. And there's a picture of Ohm over there. He looks rather worried to me. How will history remember me? Will they name a law after me? When they did. And Ohm's law is simply V equals IR. Technically, it's delta V equals IR. Usually, we just abbreviate it as voltage equals IR. We know it's the change in voltage. So V is the voltage, I is the current, and R is the resistance. Now, the resistance is even measured in ohms, named for ohm. I should just mention that Ohm's law is not perfect. When you say law, well, it works really well for metals, but it does not work for semiconductors, which are non-ohmic. Now, we need to deal with this idea of resistance. You could think about water flowing down a stream. And if you've ever been whitewater rafting, when there are a lot of rocks, and you have to be careful if there's a lot of rocks, that's resistance. The water can't flow smoothly, and you get all the bubbling and the churning and the splashing of the water. Resistors are that way too. Resistors, well, there's different color codes. You can see them over here. And people who do a lot of electrical work, they can just look at it and know exactly what the resistor is. And there's this, like you need a chart, and there's these weird ways to tell what the, green means this and red means this. And I don't know them off the top of my head. I have to look them up. But resistors tend to resist the flow of electricity. You say, well, how do they do that? How do they get rid of the electricity? It's not that they get rid of it, but some of the energy is lost through heat. So if you've ever been vacuuming for a while and you pick up the cord, to move it along, or you want to move the cord, sometimes it's warm. That's resistance. And some devices like traditional light bulbs, electric stoves, toasters, they want a lot of resistance. They have a lot of resistance built right into them, and the idea is that they want to give that off as heat. So usually you're losing this energy through heat through the resistor. Now, every wire itself has some resistance also. So let's take a look at this. A small flashlight draws 300 milliamps and it has a single 1.5 volt battery. So let's calculate the resistance of the bulb. And like I said, I just use V equals IR. You can write the delta V if you like. So R is V over I. These are really easy. The voltage is 1.5 volts. Now that's milliamps, so that's 0.3 amps. And if my math is true, let's see, 1.5 divided by 0.33 is, it says 4, I think I'm getting 4.5. What am I doing? Oh, excuse me, I forgot the zero there. Little mistake there, little math mistake. Yeah, and it is 5 ohms. And ohms has that omega sign is what we use for it. Now it says if the voltage stays or drops to 1.2 volts, and that can happen. Batteries wear out. Well, what current would flow? So V equals IR. So I would be V over R. So the voltage is 1.2 volts. The resistance is still 5 ohms. And I would be 0.240 amps. A lot of times electricians and people who do electrical work, electrical engineers, will make it into milliamps. It's just easier to say 240 milliamps. And of course, let's see, V equals IR. If you really want to, you could make that triangle. And then you cover up the variable that you don't want to, that you're interested in, the one that you're trying to solve for. Now there's a more complicated formula for resistance. And you say, well, why do we need that? This is for any wire. This lets us theoretically predict what the resistance is going to be through a wire or a particular piece of metal. And it's R is, that's the Greek letter rho, rho times L over A. Now let's take a piece of this apart. L is the length, and that's on top. So it makes a lot of sense that the longer the wire, the more wire that the electrons have to go through, the more chance there is for resistance. And that resistance comes from bumping into other electrons and the way the atoms are arranged. It really ends up being more down at the atomic level. Area. Area is on the bottom. So it turns out if you can make your wire wider, you get less resistance. It's kind of like, opening a valve. The more you open it, the more water can flow through. Or a bigger hole in a dam, more water can go through. So the wider the area, the less resistance. And rho is just this resistivity of the material. It's a property that every material like copper or aluminum or iron or any material that conducts just has naturally. Now here's the chart of resistivities. Nobody memorizes them. Unless you do this every day, you don't memorize them. So what you can see is there's different kinds of wire. Silver can be used as a wire. Copper, and they all have their particular values. Most of them are in the range of 10 to the minus 8. There are some that are really good, like this nickel chromium. Now, that's 100. So I shouldn't say really good, but really good at producing resistance. That's a much higher resistance than, say, a pure copper wire. Copper is expensive, so that's why we tend to use it for wiring. Aluminum is actually pretty good, and aluminum can be used for wiring. I have seen aluminum wiring in older homes. I think the problem with aluminum is that it also can melt and can be a fire hazard, so you don't see aluminum used too much for home wiring anymore. And then there are some numbers for things like carbon and germanium and some of the semiconductors. One thing you do note is when you get into insulators, like glass is a pretty good insulator. Very, very high resistivity value, 10 to the 14th. Quartz or silicon, 10 to the 16th. So a lot of these over here, wood, they're not going to conduct electricity very well. Super high resistance. So let's just do one of these problems and we'll probably call it a video. So we have a wire that's 10 meters. That's the length. But it's only 2 millimeters in diameter. And we want the resistance. So first order business is pi r squared, getting the area. Now watch, because I should have drawn it all the way. That's the diameter. That means that the r is actually only 1 millimeter. 1 times 10 to the minus third meters. We're going to square that. So it's going to be a really small number. The minus third squared equals times pi 3.14 times 10 to the minus 6 square meters. Now we can get the resistance, which is rho L over A. Now the rho value we have to look up, the resistivity. 1.72 times 10 to the minus 8. I had to go back and look it up myself. I don't have it memorized. The length is 10 meters. And the area is 3.14 times 10 to the minus 6. So the only thing I have to do now is crunch all these numbers in my calculator. And I'm getting a resistance of 0.0548 ohms. I didn't draw that omega very well. There we go. Or if I multiply it by 1,000, I get 54.8 milliohms.